Hey everybody, I'm Ivan Novick from Ponzu Broadcom team. Today we're here to talk about RabbitMQ with David Ansari. David, could you introduce yourself?
Hi, I'm David. I'm an engineer in the RabbitMQ core team since 6 years, and I'm working for Broadcom.
Awesome, awesome. So I'm really happy to have David here because he's been inspirational, one of the inspirational team members working on the product. And we announced the 4.2 version of RabbitMQ. And so how are you feeling about 4.2, David? What's your overall sense of the product version and what it's bringing forward?
Yeah, I'm feeling very good. It's packed of a lot of new features, one of which we are going to explore in more detail today, which has to do with SQL, broker-side filtering for streams. But there are also a lot of other interesting features coming. One highlight will be that Capri, the new metadata store, will be enabled by default for new clusters. And other highlights are also that there are new message interceptors, which allow you to intercept incoming and outgoing messages, and also a direct reply to for AMQP 1.0, which broadens our feature set for AMQP 1.0.
Right. Okay, great. So today, what I think we need to focus on is the new advancements on streaming. And as you mentioned, the SQL filtering for streams, which is very exciting. But before we get into the SQL filtering, not everybody knows what is streaming in RabbitMQ. I mean, I think RabbitMQ that's known for message queue, right? So can you just give a quick overview of when we say streaming in RabbitMQ, what did we offer in RabbitMQ for streaming and kind of what's the general landscape of that?
Yeah, so as you said, traditionally RabbitMQ, and MQ stands for message queue, has been about queuing, and streaming capabilities were introduced in RabbitMQ 3.9 4 years ago. So by now, this is a very major feature in RabbitMQ. And streams are different from queues. So streams are an append-only log, and they provide non-destructive consumer semantics. So this means that if consumers receive messages from a stream, those messages are still in the stream because it's an immutable log, right? So in contrast with queues, if you consume messages from queues, those messages are being removed from the queue. And there are a lot of interesting use cases why you would want to adopt streams. So one use case would be, for example, large fan outs, because your publisher sends a message into a stream, and then that same message can be read by many different consumers. So in contrast, if you use queues, you would need to bind one queue per consumer to an exchange, and then every queue gets a copy of that message, which also works, but it's more scalable to do it with streams. There are also other features. For example, you can do a replay and time traveling. So you can have your consumers attach anywhere in the stream by offset or by timestamp, and then they can consume messages, but they can also go back again and consume the same messages again or skip a certain time range. Streams are also there for high throughput. So we've designed our own RabbitMQ specific streams protocol, which enables you to publish and consume millions of messages per second.
Millions per second?
Exactly. And streams also provide large backlogs. So the amount of messages that you can store depend on your disk capacity, right? Because the messages are stored on the disk. And this is also a bit different from queues, because queues, they converge towards the empty state. So you want to have your queues empty as much as possible. Whereas for streams, they converge towards the full state. So the stream becomes full, and then all segment files in that stream are being deleted over time, depending on how you configure your retention policies. So you can, for example, say you want the stream to be available for 1 week, then all data older than 1 week are being automatically deleted. There are a few more use cases for streams. For example, they provide strict message order because, again, the stream is immutable. And this is different with queues, right? If you have multiple consumers from the queue, then one consumer can requeue the message, it can discard messages. A consumer can have network connectivity issues, so it disconnects and the messages are automatically requeued that were previously checked out by that consumer. So messages might get out of order if you don't pay attention. There are ways to have strict message order also with queues. For example, if you use the single active consumer feature, but then you only have a single active consumer. So with streams, you have strict message order by definition, but you can have multiple consumers. And then one last aspect I would like to mention about streams is the protocol interoperability. It's very nice in RabbitMQ. So you can use any protocol to publish to a stream, for example, AMQP or the RabbitMQ streams protocol, but also MQTT. So you can have IoT devices which publish into a stream. So interoperability is one of the strengths of RabbitMQ.
It's a bit mind-blowing how much capability there is there. Now, from a performance point of view, you said it's millions per second. So I'm presuming that means that's faster than if you were to use message queues, right?
Yes, exactly. And that's because streams under the hood, they transfer entire chunks. So we'll talk about what a chunk is later on in more detail. And they use, for example, the send file system call. So the broker will dispatch entire chunks without reading any data into user space, into memory. So this is very efficient. And with the other message queuing protocols, for AMQP or MQTT, they are message oriented. So they are based on a per message level. So the broker needs to pass each individual message and then sends it to the client. So that's why streams are much more performant.
Gotcha. So for any kind of high volume, multi-consumer data, especially replaying and reprocessing data, right? Then streams will be the perfect, ideal way to go.
Exactly. Yeah.
And that's different than if you're building a microservice application, for example, where you put in you process in e-commerce, you process a order and then you send a message to the email service saying, hey, send an email to the customer. That's kind of a different pattern. There are many patterns where message queuing is better. Maybe you should just mention under what condition would you really want to use queuing instead of streams?
Exactly. So it really depends on the use case. So queuing is useful if you have, for example, certain jobs that need to be processed or one-time events that need to be processed. In this case, you don't need to hold on forever in the broker for that particular message. You just want to make sure that your publisher sends some information and then some consuming application are processing it. So as soon as one consumer processes that message, it gets acknowledged and then immediately deleted in RabbitMQ.
Got it. So that's more efficient in that case. Okay. So let's get back to 4.2 and let's get back to the SQL filtering. So can you introduce what we've provided with the SQL filtering? What's the use case? What's the capability?
Yes. So yeah, just yesterday, we published a new blog post describing that feature. So it's about broker-side SQL filtering for streams.
And are you going to mention why you emphasize broker side instead of just SQL filtering in general?
Exactly. So the main motivation is that you might have a lot of different event types in one specific stream. So for example, stock tickers or regions or tenants or SKUs or different types of
let's say stock tickers, for example. So if you're processing stock price updates, right? And you have thousands of stocks, for example.
Yeah. In that case, for example, you might have some consuming application which are only interested in processing one specific stock. So let's say Broadcom, right? So in this case, I mean, if you have only, let's say, 3 stocks, what you could do is you create 3 streams. And then you have what's called a super stream or a partition stream. And then you make sure that each stock gets into its own stream. But if you have like 10,000 different stock tickers, then this becomes unscalable. You cannot create 10,000 different streams efficiently.
Agreed. And normally you'd want to you'd have all the feed that has all the stocks coming as one at the center point.
Exactly. And then If one consuming application is, let's say, only interested about the Broadcom stock, then what it would need to do traditionally is consuming the entire stream onto the client side and then do the filtering on the client side. So filter out only the Broadcom stock on the client side. And as you can imagine, this is highly inefficient because the entire stream needs to be transferred to the client, which wastes gigabytes of network bandwidth. So this is where broker-side filtering becomes relevant. If you have this kind of low selectivity use cases.
And broker side also means server side, right?
Exactly. So that's the same thing. Yeah. When I say broker side, I mean server side. Yeah.
Okay.
And we also wrote an entire new documentation page for RabbitMQ 4.2, which explains stream filtering in more detail. So I tried to provide one picture.
Yeah, let's try and understand it.
Yeah, I tried to provide one picture which explains the different filtering stages. So in the upper yellow box, this is everything happening on the broker side, right? So on the RabbitMQ server node. In the lower yellow box, this is all happening on the client side. And in between, you have the network, right? And as you just said, traditionally, if you want to do filtering, you would consume all the messages from RabbitMQ from that particular stream and do the filtering client side. This could be either in a client library or in your client application. So this is what we call here stage 3. And again, this is highly inefficient if you have low selectivity because it wastes network bandwidth, but also a lot of client CPU memory usage.
For sure.
This is where server-side or broker-side filtering becomes relevant. And for that, RabbitMQ provides a stage 1 called the Bloom filter. This operates on the chunk level. And what's new in RabbitMQ 4.2 is stage 2 SQL filter expressions. Now, should we first talk about the Bloom filter and what chunks are in a bit more detail?
Yeah, let's do that.
All right. So in order to understand what chunks are, let's go a bit up and understand how, on a high level, messages are stored in a RabbitMQ stream. So the on-disk stream layout looks as follows. A stream consists of multiple so-called segment files. A segment file can have multiple chunks, and a chunk can have one or multiple messages. Now, a chunk is the lowest level of granularity, for example, that RabbitMQ uses to replicate messages to other stream replicas, or also the lowest unit that RabbitMQ uses via the RabbitMQ stream protocol to deliver messages. So via the RabbitMQ stream protocol, only chunks are being delivered to clients, not the individual messages. And it depends on the ingress rate how many messages there will be per chunk. So for example, if your publishers publish very quickly into the stream, you end up with many messages per chunk. If your publishers send very slowly, you end up with only a single message per chunk.
Okay. But in our high-speed trading case, we're going to have tons of messages coming in per second, right?
Yeah. Then we would likely have multiple messages per chunk.
Correct.
Okay, so each chunk also has what you see here, a header. And this is where RabbitMQ stores the Bloom filter data structure. Now let's talk about the Bloom filter, how it works. So we have the publisher, which sends messages, right? For each message, it can optionally set a Bloom filter value. For example, in our case, it's the stock ticker.
You're saying that the client that is trying to read the stream can set the Bloom filter?
Exactly. So both sides. First, the publisher, it sets a Bloom filter value per message.
Okay.
And then later on, the client, when it attaches to a stream, it can also optionally provide a Bloom filter value with only those messages that it is interested in processing.
Cool.
Exactly. This is how it works. And one more detail. So if RabbitMQ accumulates, sufficient messages, it will collect all the different Bloom filter values of those messages and put it into a single Bloom filter data structure and write it into the header. And only then it's going to write all that chunk worth of messages to disk.
Okay.
Now, this is important because if now the client attaches, so the consuming application, and says, for example, I'm only interested in the Broadcom stock, then what RabbitMQ will do is it will only read the header of the chunk from disk. And if it knows, based on the Bloom filter, which is a very efficient probabilistic data structure,
Correct.
if RabbitMQ knows no message in that chunk is about Broadcom, then it's going to skip the entire chunk worth of messages.
And hence it won't provide it to, and it'll skip that data and not give it to the client as well.
Exactly. And it also won't read any messages from disk at all. So there's no disk I/O going on to read the message header or message payload.
So there's two benefits actually, right? So it's going to make reading the stream faster on the broker side, but also it's going to reduce what's sent to the client to filter and process, right?
Correct. Exactly.
Okay.
So
how would that compare to somebody doing the exact same thing, trying to read from Kafka with a stock exchange and wanting to only process one stock?
So in Kafka, you would need to read the entire stream worth of messages. And this means high network bandwidth, or Kafka also has something like KSQL. And this will derive you a certain other stream based on some SQL expressions. But also for KSQL, those queries, those filtering does not run on the Kafka broker. It runs on separate machines. So you still have a lot of network bandwidth, which is going on between Kafka and the KSQL database.
So it doesn't do the broker side filtering?
Exactly. So Kafka does not support broker side filtering.
Okay. Okay. All right. So let's continue.
Yeah. So the Bloom filter is the most efficient filtering stage, and this is stage 1. So this is now what we understand. And if the entire chunk matches, then you can send, you can receive via the RabbitMQ steering protocol, and then you need also an additional level of filtering because, as we said, the Bloom filter operates on the entire chunk level, right?
Yeah.
So you might still have messages which your client is not actually interested in. So exactly. So your chunk of messages that you receive might not contain only Broadcom stock. So you will need to combine it with stage 3 and additionally perform client-side filtering. And this is what our Java client library, for example, provides.
And by the way, can you show the code where in a client how you would set the Bloom filter?
Yes. So this is the sample application. And you know what? Let me quickly start the sample application first because it needs a few seconds to run.
You're going to actually do a live demo?
Yeah, exactly. So this is the sample application. Let's first start RabbitMQ, a single node in Docker. So this is the latest RabbitMQ 4.2 version. So it's beta 3. And then we start the client in a separate window. And then let me tell how the client looks like.
The client, and your client is in Java?
Exactly.
But client can be in many languages, right?
Yes. So RabbitMQ has many different client libraries in different languages. And this example is just in Java.
Yes.
So in our client application, we just declare a stream, and then we publish the messages. In this case, we publish 10 million different messages. And let me show you where we set the Bloom filter value. So the Bloom filter value gets set here. So we have the publisher. We create a message with a specific payload. We give it a priority. And this is where we set the message annotation. So it's called extreme filter value. And in our case,
so this tells you which value you can filter on with the Bloom filter?
Exactly. Yeah.
Okay.
And in our case, we are simulating here an e-commerce platform. So we have different event types. For example, product search, product view, cart add, cart remove, and so on.
Yeah.
And our client application publishes an order created event every 100,000 messages.
Okay.
So it's pretty rare.
Yep.
And this means we have exactly 100 order created messages in our 10 million messages stream.
You want to only read in your case, you're going to only want to read the orders, not just that they're looking and viewing products.
Exactly.
Nice.
And even less, not only the order created one, but in our case, we also create an SQL filter, which is shown here in the top. We only want to read a subset of the order created messages.
Oh, wait,
so we
wow.
first
So you're doing full SQL, not full SQL, but this looks like real SQL language.
Exactly. So this is just one example of an SQL query that you can now do in RabbitMQ 4.2. And this SQL query gets also evaluated broker side.
So it's not only looking at the Bloom filter field, it looks like it's looking at all the field.
Exactly. And this is where stage 2 comes into play.
Okay.
So stage 2 is what I'm showing right now. So this is an SQL filter expression.
Okay.
And let's try to understand what that SQL filter expression is doing. So first we want to filter on the subject being order created, as you suggested earlier, right?
Yeah.
But not only that, we also want to say that we want only receive messages whose creation time was in the last hour.
Okay.
And this is just an example, but what I would like to show here is that you can have comparison operators in your SQL query. You can even have a function. So that's a UTC function, which gets evaluated broker side and gives you the current timestamp in milliseconds. You can do subtraction. And then we also want to make sure the order is in one of those 3 regions. So we use the in SQL keyword. And we even do or semantics. So we say the priority should be high, or the price should be high, or it should be a premium customer.
Nice. How many different functions are available? You called UTC, but what functions are available?
Just this one for now.
Okay. All right.
So the spec, so this SQL syntax is based on an official standard. It's not something that we invented. It's an AMQP standard.
Okay.
So let me show you. So if I go to SQL filter expressions and click on this link here, then you see the standard being defined here. And if you scroll up, then you see that this is an official AMQP extension specification, which were relatively new, published in 2021.
Right. And so there are some other, we won't name names, but there's some other implementations of other products that might implement AMQP with SQL filter. It would have the exact same syntax.
Exactly. So for example,
there's 7 functions: lower, upper, left, right, substring. So all these, theoretically, we could add these to Rabbit later.
Exactly.
Nice.
Yeah. So, okay, let's go back to our application. And now let's go to the consuming part.
Yep.
So we first published those 10 million messages, right? 100 of them are order created, and only 10 in total match this filter expression.
Okay.
And now we consume all 10 million messages, or we try to consume them. Actually, we consume only the 10 matching ones, right? Because we use the SQL filter. But we attach at the very beginning of the stream. So we go over all 10 million messages. We are going to filter all 10 million messages.
Where's the Bloom filter registered on the client?
Yeah, that's happening in the consume messages method. So let's go to that one. And it's happening here. So it's that simple. You have a consumer builder. We say we consume from the very start of the stream. So in real world use case, you would probably attach to the end of the stream and then filter on new incoming messages. But for the sake of this example, we go from the very start. And then we just set the Bloom filter value. So this is now the consuming part. We'll say builder filter values order created.
Okay.
And this is how we set the SQL filter. Very simple. .filter.sql, and we provide our SQL string that we saw above. And that's it.
Okay.
Now what
Now,
we're going to do is
are you going to run it?
Yeah, we ran it already, but we consume those messages the first time only with the SQL filter. So only stage 2, which is only this part in our picture, right?
Yep.
And the second time, what we are going to do is we combine the Bloom filter with the SQL filter.
And by the way, was the Bloom filter available before 4.2? I know the SQL filter is the new feature, but what about the Bloom filter? Was that there before 4.2?
Yeah, the Bloom filter got introduced in 3.13.
Okay. Got it. So if you already have 4.1, you can use the Bloom filter already. SQL filter is the new one.
Exactly.
Okay.
So again, first we use our only SQL filter, broker side. Second, we combine both Bloom filter and SQL filter. So we combine stage 1 with stage 2. Also, everything runs broker side.
Yep.
So let's look at our results. So this is the sample application. It's now completed. So we first declared the stream called custom events. Then we published 10 million messages into the stream.
Okay.
As we said earlier, 100 are of type order created, but only 10 in total match our SQL filter, which our consumers use. Now we start the first consumer. It gets exactly those 10 messages as expected. And it takes 23 seconds to complete. And this is a filtering rate on the broker of more than 400,000 messages per second.
Okay.
And if you think about it, this is already...
It's running on your laptop, right?
Yeah, so if you think about it, that's already quite impressive, right? Because what happens here is that RabbitMQ parses each message from disk and runs the entire complex SQL expression, which is seen here, on the broker. And it does so at more than 400K per second.
Yep.
Okay, so now next we start the second consumer and we combine Bloom filter and SQL filter. Again, the same SQL filter, but this time in addition, we set the Bloom filter, which...
so in the first example, you didn't set a Bloom filter.
Exactly.
Okay.
The first example did not use this Bloom filter here. In the second example, we set it additionally to the SQL filter.
Yep.
So this time we again get our 10 messages, but we get them in just about 2 seconds.
Wow.
And this means we have a broker-side filtering rate of almost 5 million messages per second.
Wow.
And this shows the entire beauty, right, of combining both features. So if you are able to design your applications that you can combine Bloom filter and SQL filtering, you really get the best of both. Like you get the efficient chunk level filtering at stage 1 to skip the unnecessary disk I/O, CPU, and memory usage on the broker, followed by per message level filtering with those complex SQL expressions at stage 2. And it all happens on the broker.
Yeah, this is practically a computer science lesson on algorithms and speed.
Exactly. So this is, yeah, one of the RabbitMQ 4.2 release highlights. We can talk a bit more, if you want, about the SQL syntax that's supported.
Okay.
But we also documented it because it goes very much into the details. But basically, you have different operators and or not. You can have different keywords in, is, null. You can even have like, where you can pattern match on string prefixes or suffixes. And it somewhat leans on the JMS syntax. And as you saw earlier, we have functions, and then we can filter on different message metadata.
Right. This is great. No, this is great. So I think in summary, the 4.2 RabbitMQ with SQL broker side SQL filtering. The thing I want to come back to is that this is even, you know, as even the RabbitMQ is not as well known as Kafka for streaming data use case. It's well known for message queue, but it seems to me that this is even more efficient than what you get with Apache Kafka when it comes to, especially with the broker side filtering, right? So just to double click on that again, right? So in Rabbit, I can have a lightweight system that, help me understand, right? I can have a lightweight system. If I set up a broker side filtering, I can have many clients reading the data and they'll be very lightweight. Whereas doing a SQL expression on Kafka, it's going to always pull data off the broker and then start doing it downstream. Can you
That's
just,
correct.
yeah.
Yeah, that's correct. And it's important to again highlight that the most efficient filtering stage in RabbitMQ is that Bloom filter, and that's also available for the stream protocol.
Right.
So this is what's depicted here, right? You can use the Bloom filter just with the stream protocol, and then you get high throughput and still very efficient.
So I think the message
broker
out
side filtering.
to all the RabbitMQ users out there is you don't need to look elsewhere if you have a streaming use case, right? If you've got RabbitMQ and you want to do data streaming, this is a world-class solution, right? And so
Yeah,
RabbitMQ itself, you're already handling message queuing, but it can handle streaming as good or better than every other platform out there. And so you should look no further than RabbitMQ for your huge data streaming use cases with, I mean, as far as data size, right, this will scale to, I assume this will scale to, what will it scale to? How much data, is it scaled to multiple nodes?
yes, so a stream can be replicated to multiple nodes. So by default, I think it's to 3 nodes, but you can also have a super stream. So super stream is something which we introduced in RabbitMQ 3.11. And a super stream is a way to scale out publishing and consuming by partitioning the stream. So
Okay.
my colleague Arnaud wrote very interesting blog posts, which I recommend to read. So if you go onto the streams tag
Yep.
and scroll a bit further down, then you see here an introduction to super streams and what they're good for. So it's basically a way to scale out publishing and consuming to multiple RabbitMQ nodes.
Yes. Great. All right, David, thank you so much. So everybody out there, look forward to the RabbitMQ 4.2 release. It's amazing work and it's amazing product. So thanks everybody in the community for giving the feedback, and we'll see you on the next stream, so to speak.
Thank you very much.
All right.